Welcome to today's paper reading. Today's paper is titled, Quantifying Language Models Sensitivity to Spurious Features in Prompt Design, or How I Learned to Start Worrying About Prompt Formatting. This paper, presented at ICLR 2024, examines the sensitivity of large language models to prompt formatting by Yejin, Choi and colleagues from the University of Washington and the Alane Institute for Artificial Intelligence. The abstract highlights the sensitivity of large language models, LLMs, to prompt formatting, which can significantly influence their performance. Specifically, the study finds that even subtle changes in prompt formatting can lead to performance differences of up to 76 accuracy points, particularly in few-shot settings. This sensitivity is observed even when increasing the model size or the number of few-shot examples. The abstract also points out methodological issues, such as the weak correlation of format performance between models, questioning the validity of comparing models using a fixed prompt format. To address these issues, the authors propose the Spurious algorithm, which evaluates a range of plausible prompt formats and reports the expected performance intervals without accessing model weights. This approach aims to facilitate more systematic and comprehensive analysis of LLM performance. The introduction of this paper discusses the sensitivity of large language models, LLMs, to various prompt features, particularly focusing on formatting choices. It highlights that despite the assumption that formatting should not significantly affect model performance, there are unpredictable accuracy variations, with up to 76-point differences observed in some cases. The paper introduces the Spurious tool, which systematically analyzes these variances using Bayesian optimization, allowing for efficient exploration of prompt formats within a computational budget. This tool reveals significant accuracy spreads, up to 56 points, across different formats, emphasizing the importance of considering formatting choices in model performance evaluations. Figure 1 illustrates how minor changes in prompt formatting can lead to substantial variations in model performance. The example provided is based on one-shot performance of Llama 2-7B for task 280 from Supernatural Instructions. This task, inspired by StereoSet, involves classifying a short passage into one of four categories: gender, profession, race, or religion, stereotypes or anti-stereotypes. Each text placeholder in the figure represents a variable length segment to be replaced with actual data samples, highlighting the sensitivity of model performance to these formatting details. The evaluation of LLM performance is conducted over a space of prompt formats that a non-adversarial user might choose for a target task. This space is defined by a grammar, which also induces a definition of semantic equivalence among formats. The model's sensitivity is quantified by the performance range across semantically equivalent formats. The problem of searching this space is cast as a bandit problem, and Spurious is proposed to address this. Format spread includes a grammar and a procedure to estimate performance across equivalent formats using Bayesian optimization, all without needing access to model weights, thus enabling use on API-gated LLMs. The authors construct a grammar manually to ensure precision in defining the space of plausible prompt formats and semantic equivalence between formats. This grammar is tested on over 100 tasks to verify its effectiveness. The grammar consists of basic fields and rules for joining these fields to create prompt formats. The equivalence of prompt formats is formally defined, ensuring that sets of equivalent formats share the same semantic meaning. This equivalence is crucial for the sensitivity analysis conducted in the study. To measure sensitivity, the authors define the performance spread as the difference between the maximum and minimum performance across different formats. They focus on task accuracy as the primary metric and employ a multi-arm bandit approach to efficiently explore the space of plausible formats. The study utilizes a subset of 53 tasks from Supernatural Instructions, including 19 multiple choice and 34 classification tasks. Models evaluated include Llama 2-7B, 13B, 70B, Falcon 7B, and GPT 3.5 Turbo. Task evaluation metrics include exact prefix matching and probability ranking, with ranking accuracy typically reported. The analysis reveals a significant performance spread across tasks, with a median spread of 7.5 accuracy points. Notably, 20% of tasks exhibit a spread of at least 15 accuracy points, and significant spread is observed regardless of model size or the number of few-shot examples. Figure 2 illustrates the spread in performance when evaluating the same task under different models or n-shot learning conditions. This comparison helps in understanding how variations in model size or the number of training examples, n-shots, impact task performance. The spread analysis provides insights into the consistency and reliability of model evaluations across these different settings. Figure 3 illustrates the performance spread across different models and the number of few-shot examples, n-shots. The data reveals a median spread of 7.5 accuracy points, indicating significant variability in model performance based on prompt formatting. Notably, 20% of the tasks exhibit a spread of at least 15 accuracy points across all model settings, highlighting the substantial impact of prompt formats on model outcomes. The spread remains significant regardless of the model size, reinforcing the importance of considering prompt format sensitivity in model evaluations. Figure 4 illustrates the probability that a model M performs worse than another model M by at least a specified difference d when using a different format P, given that M initially performed better than M by at least d using the original format P. This analysis covers 53 tasks with both 1-shot and 5-shot evaluations. Key findings include that Llama 2-13b and -70b reversed their performance trend by at least 0.02 with a probability of 0.141, and Llama 2-7b and Falcon 7b reversed by the same margin with a probability of 0.140. Notably, 76% and 47% of these reversals were statistically significant on 1,000 samples, indicating that the choice of format can significantly alter model performance comparisons. Table 1 illustrates the tasks where at least two constants yield different performance, categorized by weak and strong differences based on box plot overlap. The table provides median spread values and percentages of tasks showing weak and strong differences for various constants such as separators, S1, number format changes in enumerations, FIDEM2, and casing. Table 2 illustrates the significant impact of atomic changes on accuracy using probability ranking. Each example shows a different prompt format, P1, and its modified version, P2, where P2 consistently achieves higher accuracy. The table highlights how small changes in prompt formats can lead to substantial differences in model performance, emphasizing the importance of careful prompt design. Figure 5 illustrates the distribution of accuracy for 500 sample prompts, focusing on the choice of S1, the separator between a descriptor and the text placeholder, in one task from supernatural instructions. The figure highlights how different choices of S1 independently influence task performance, using both weak and strong notions of dissimilarity to measure the differences in accuracy distributions. Weak dissimilarity is observed when the first and third quartiles do not intersect, while strong dissimilarity occurs when the ranges of the distributions do not overlap, including the whiskers of the box plots. Figure 6 illustrates the probability that making an atomic change, such as altering a space or separator, results in a specified impact on accuracy using two different scoring criteria. Specifically, it shows that 24% of such changes lead to an accuracy change of at least 5 points when exact prefix matching is used as the scoring criterion, whereas only 11% of changes result in a similar impact when probability ranking is used. The analysis covers 53 tasks, each with 30 sampled atomic changes, highlighting the variability in accuracy changes due to minor formatting adjustments. Figure 7 illustrates the cumulative ratio of tasks that can be classified with a certain accuracy using the top principal components of the last decoding layer of the prompt. This figure highlights how the number of principal components correlates with the ability to accurately classify tasks based on their prompt formats. Figure 8 illustrates the probability of observing a spread increase of at least d when the sample size is increased from K1 to K2 formats. This analysis was conducted across 31 tasks, each with 100 trials, providing a robust dataset to quantify the expected spread increase with varying sample sizes. Figure 9 illustrates the difference between the true sample spread and the spread estimated by each algorithm, Thompson sampling, UCB, and naive sampling, with respect to the evaluation budget E. With a budget of 51,200 evaluations, Thompson sampling achieves a spread within 1 accuracy point of the true spread, naive sampling within 4 points, and UCB within 11 points. This comparison highlights the efficiency of each method in estimating the spread of the highest and lowest performing formats. The task of optimizing prompts for best performance without altering model parameters has seen various approaches. Gradient-based methods, such as those used by Shin et al. 2020, are effective but can produce unnatural prompts, which can be mitigated by Langevin dynamics-based methods like those proposed by Suhr et al. 2022. Another approach involves learning and optimizing continuous representations of prompts, as done by Cheen and Eisner, 2021, and Lester et al., 2021. However, these methods require access to model parameters and cannot be applied to models behind an API. In contrast, gradient-free methods, such as edit-based enumeration by Prasad et al., 2023, reinforcement learning by Ding et al., 2022, and LLM-based methods by Zhou et al., 2023, focus on achieving competitive performance even with modified prompts. Our work, FORMATSPREAD, is unique in focusing on prompt formatting variants, a form of semantic equivalence. Additionally, while jailbreaking studies like those by Wei et al., 2023, and Zhou et al., 2023, aim to find the lowest performing prompts, our methods differ as they do not rely on human-generated attacks or gradient-based search across multiple models. Other related work has explored the influence of prompt design choices, such as language, example ordering, and patterns, as well as the interpretation of continuous prompt representations. Our work also aligns with efforts in other domains that examine the impact of spurious features on research evaluations. The authors introduce FORMATSPREAD, an algorithm designed to estimate the performance spread across different prompt formatting choices. This tool is used to evaluate the spread of several widely used open-source large language models, LLMs, in classification tasks under few-shot learning settings. The findings indicate that the spread is significant regardless of model choice, even when adjusting factors like model size, number of few-shots, or instruction tuning. Format spread is efficient, capable of estimating spread within 2 accuracy points of the true spread with a computational budget exploring only 5% of the search space. The authors also characterize the space of prompt formats, noting it is largely non-monotonic and that few atomic features can predict performance alone, though format embedding separability is highly correlated with performance spread. These insights inform the design of the search procedure, which avoids local search methods. The implications of these findings suggest that performance spread due to arbitrary prompt formatting choices can influence conclusions about model performance, particularly when comparing models on benchmark tasks. Therefore, the authors recommend reporting a range of performance across plausible formats in evaluations. However, they acknowledge that single-format evaluation may still be sufficient for many use cases. They encourage future research to use FORMATSPREAD when comparing systems to out-of-the-box models to ensure fair baseline representation and to identify lower-bound performance, especially in socially impactful tasks. The authors expressed their gratitude to Gillian Fisher, Sachin Kumar, and Angela Zhou for their valuable discussions. The Berkeley NLP group also contributed significantly to this work. The research was conducted while AS was a young investigator at AI2. The project was partly funded by the DARPA CMO under contract No. HR 001120C0124, the DARPA MCS program through NIWC Pacific, and grants from the NSF including DMS 2134012 and IIS 2125201. Additionally, an Alfred P. Sloan Foundation Fellowship supported this research. The opinions and conclusions expressed in this material are those of the authors and do not necessarily reflect the views of the United States government or any agency thereof. Thank you for watching.